Let's start with this problem. So I'm going to show you two solutions, two different methods of calculating the problem we left off with on Wednesday's class. And then the warm-up vote is going to just be which one did you like better. That's the kind of a fun way to start our Friday. And so we had this situation of 3 red balls and 2 white balls in an urn that we've been looking at for a while now. And we drew the tree, we did a whole bunch of things. And now we're trying to do a calculation of what is the probability that the second ball is red, which in our notation was P of R2. The R2 means red on the second ball. And it turns out that this is, if you work it out, which we're going to do 2 different ways, the answer is 3/5. 3/5. Which is kind of like what there's 3 red balls, or there's 5 balls total, and it's 3/5. So it's maybe like not surprising. But the thing that makes it annoying is that it's the second ball. And we saw that the second ball depended on the first ball. So that's quite annoying. And so when you go to work this out, there's sort of 2 different ways you can do it. You can kind of do it the straightforward way. That's going to be method 1. Method 1. Actually, why don't I make this full screen for now? Method 1, which I call the straightforward way. Doesn't mean it's easy, but it is straightforward. And that's just we're going to draw the whole tree and figure it out. Draw a whole tree. And we're just going to do it the sort of like mundane way. We're going to draw the whole tree. We're going to figure out how to do this. And it's going to work out to 3/5. And then we will move on. That'll be perfectly correct. But after method 1, I'm going to show you method 2, which is like a little bit more kind of thinking and clever. And it's going to try to explain why is it 3/5, which is what you would expect. But method 1 is really what we've been doing the whole time. So there are 4 possibilities, right? You could get 2 red balls, red, red. These are the 4 options. You can get a red on the second one, or a red on the first one, or no reds. Let me draw in the white balls. So these are the 4 possibilities. And the thing is, when you draw them, they're not all equally likely, right? Like when you flip coin flips, because of the symmetry between heads and tails, if you flip 2 coin flips, all 4 possibilities would be equally likely. But when you're drawing them from this funny urn, they're not equally likely because there are 3 red balls. And also, once you start drawing balls without replacement, you don't put them back, the odds change. So that's why we need our whole tree. But fundamentally, there are 4 possibilities. We're going to calculate the probability of each one. And then the chance that there is a ball that is red on the second one, R2, is this event, right? R2 is this one and this one. This one is R2. R2. So if I can calculate the probability of all the individual pieces, then I can use the disjoint sum rule to say, look, if you got a red ball on the second one, either you got red, red, or you got white, red. And then we'll do it that way. So that's the straightforward, that's the idea. And in fact, our probability tree is essentially these 4 outcomes. Our probability tree has 4 outcomes corresponding to these 4 things. So let's draw the tree. I'm going to draw my tree. I'm going to be controversial and draw my tree up, down. Because in real life, trees go up and down. Of course, in math class, they go the reverse way. But let's not worry about that. So here's the start. And we draw our first ball. And our first ball can either be red or it can be white. So we either get red first or we get a white first. White ball first. And we know the probabilities are 3/5 and 2/5, which is nice for the first ball. And in fact, look, like we've taken the universe of all possibilities and it has split into 2, either a red on the first or a white on the first. And we can do that in our picture as well. Those are the columns, right? So this column, like this piece of the universe, let me draw it like this, and then this piece of the universe. On the left half of the universe, it has probability 3/5, and then the right half of the universe, probability 2/5. So there's a 3/5 chance you're here or here, those 2 possibilities, and there's a 2/5 chance you're here or here. So the probability tree splitting into 2 is like taking all the things that can happen and splitting it into 2 and saying what are the probabilities. And then from there it splits again, right? So the probabilities, given that you have a certain thing, like the red ball on the first, then we know the situation and we can calculate what happens. This is kind of an if-then statement. So if we drew a red ball first, then when we go to do the next thing, it can be a red on the second, or it can be white on the second. And the probabilities are no longer 3/5, 2/5, because now there's a different composition of balls there. So how many balls are there? Well, there were 3 red and 2 white, and we took out 1 red one here, and we didn't put it back. So by my math, there's 2 of each. So I think this one is 2 quarters and 2 quarters. Someone correct me if I'm wrong. Is that right? Okay, some people are nodding. And what we're saying is, look, the left half of the universe, the 3/5, actually also splits into 2. Again, so it kind of has a second subdivision here, which I'm going to draw vertically like this. So this is split into 2 pieces. And in this case, the 2 pieces, right, there's red, red, that's this piece, and there's red, white. And what we're saying, these 2 quarters are saying that each piece should be half 2 quarters of the whole piece, right? And this is the multiplication rule. If this piece over here, this little chunk in the corner, is 2 quarters of the whole thing, and the whole thing is 3/5 of the whole thing, then the probability multiplication rule says the probability of this guy is 3/5 times 2 quarters, also known as 6/20. I'm big into not simplifying my fractions. I like 6/20. Okay, so the probability of red, red is 6/20. That's what we've seen a long time, but now we're kind of visualizing it a little bit differently. Okay, and similarly, this one will also be 6/20, 3/5 of the big blue on the left times 2 quarters for the bottom bit is 6/20. On the other side, things also split, but the split is a little different. So we removed a white ball, so I think it's 3 quarters to be red and 1 quarter to be white. And so this one splits as well, but the split is now uneven, so it's more likely to be red than not. So I'm going to draw it kind of like this, like this. So then this one is 3 quarters times 2/5 equals, again, 6/20 by some weird coincidence. And then this one down here is 2/5 times 1 quarter, which is 2/20. So altogether, we have 6/20, 6/20, 6/20, and 2/20. And so this is a probability space with unequal outcomes. And by using the probability tree, we can calculate all the possible things. So far, this is all review from the last few classes, but just kind of represented a different way that is maybe nice to see. In practice, you just think about this in your head, and then you just draw the tree, right? And then you do all the calculations on the tree. This sort of like extra stuff is just to help us think about. And it's going to come up a little bit in method 2, which is the main reason I'm drawing it. But any questions or comments so far about this stuff? I was going to wait till the end, but I'm so excited I cannot wait, which is that you have a homework assignment on probability trees that is due next Friday. So this one on probability trees. These 2 are due today. Make sure you do them. They're all stuff from previous weeks, like special words and like basics about dice. But the next one on probability trees is due next Friday, and it has all sorts of funky questions just like the one we're doing. Here is an urn problem where when a ball gets taken out of the urn, it's replaced with some weird combination. In this one, the color of the ball is noted, and it is replaced with 2 balls of the opposite color. And you have to make your probability tree, and then you have to calculate all sorts of things. All the things you have to calculate, you can calculate them by first making the probability tree, and then using all the rules we've been talking about, like adding rules, conditional probability rules, and so on. And there's a nice little description here that tells you how to do these problems. And all the numbers are randomized. So when you do it, you'll get a different question than anybody else. Once again, I think it's really important I cannot overstate, the purpose of the homework is for you to learn the material. This question is quite a bit harder than the one we did in class. It should feel very difficult. But when you sit down and do it, you're going to go, hey, this is harder than the one we did in class. Professor Humphrey was talking about this last class, but I think the big difference between high school and university math, in high school, there's like a problem, and then you learn how to do that kind of problem, and then you see that kind of problem, and then you go, oh wait, that's the problem we did before, and then you do it. In university, when you see a problem, your first reaction should be, I have no idea how to do this. And then your second reaction should be, let me try some stuff. What are the tools that we learned in class? Oh, we learned about probability trees. We learned about adding probabilities. And you take all the tools, and you construct a new solution to a problem you've never seen before. So the difference is, in high school, when you see a problem, you know how to do it. In university, you don't know how to do it, but you hopefully have the tools. And you use all the tools together. You turn the screwdriver this way. You use the pickaxe like this. And you eventually get to the solution. It's not going to be the first thing you try. Maybe it's tricky. OK. That's the homework. Why am I telling you this now? Well, I want to motivate you to pay attention for the rest of the probability tree question, because it will help you out in the homework. Questions or comments about this or anything else? OK, let's go back to our problem and finish it up as promised. So next up, we want to calculate the probability of R2 that there is a red ball on the second. And like we said, R2 is the top row over here, the top row. So this is R2, is this one and that one together. Maybe I'll color it in like this. And now we use the disjoint adding rule. So we've calculated the probabilities of each one individually. And the disjoint adding rule says the probability of R2, there's two ways R2 can happen that are disjoint. Either we get red-red or we get white-red. So you could write this as probability of, if you want to be really fancy, you could say red-red is R1 intersect R2. White-red is R1 complement intersect R2. And then these two things are union together. So you can do this fancy thing, which is a complicated soup of symbols that says it's that or that. And they are disjoint. And now we add them together. So this is the probability of red-red plus the probability of white-red. Okay. And very often in probability, you do this thing where the thing you actually want is made of lots of pieces, and you add up all the pieces. In this case, it's going to be 6 out of 20 plus another 6 out of 20, also known as 12 out of 20. And now I'm terrified. Is 12 out of 20 the same as 3/5 that I promised? Okay, thank God it is. Okay. Whew, close one. 3/5, which is what we said. So that's this is a straightforward way to do it. A lot of the homework problems will be like this. You do the whole tree. You figure out what are the parts you need. This kind of soup of symbols, you don't necessarily need to write down. You can just say, oh, the probability is that plus that. That makes sense. Questions or comments about the straightforward way? Okay, so now here is the fun part, which is method 2. I call it the tricky thinking way. Method 2. And method 2 starts with a kind of a thought, which is, of these 4 balls, we got red, red, white, red, red, white, and white, white. That could come out. Well, the question, we're only asked about the second ball. So what if I was to close my eyes when the first ball was being drawn? So imagine I'm there, and I'm just going to cover up the first ball. Like imagine you don't know what the first ball is. So I close my eyes, I reach into the air, and I draw the first ball. And then I put it behind my back so I never look at it. And then I draw a second ball. And the thing is, because you imagine there's the balls that are left in the air, and there's the ball behind my back. But I don't know what it is. So how is that any different than just drawing a first ball? You see, so this kind of thought experiment is kind of saying that drawing the second ball, as long as you don't look at the first ball, should be the same as drawing the first ball. So this is the idea. This is the idea that makes this whole thing tick. Drawing the second ball. And mathematicians like to use a word, morally. Morally the same. Morally the same as the first ball. As long as you don't look. So this is a great idea. And therefore, you should expect that the probability of the second ball being red is the same as the probability of the white ball being the first ball being red. I'm going to put equals question mark because we haven't actually figured this out yet. But if so, then it's just 3/5 because that was the thing we did. And that's easy because we know that was the only one piece of one branch of the tree, 3/5. So that's the idea. And if you get used to these things, you can convince yourself the idea is true in a number of ways. And the way I'm going to sort of prove it to you, this is a part of formal mathematics, is you take ideas and you turn them into rigorous proofs. And in this case, what I'm going to do is I'm going to construct a function that proves that this is true. So here is that was the idea. And this is the actual rigorous proof. The proof is we're going to make this idea rigorous with a function. And the function, we're trying to prove that the first ball and the second ball are kind of interchangeable. Like if you flipped everything, right? If you thought of the second ball as the first ball, then you could think of the first ball as the second ball. Actually, you can imagine I have the ball behind my back, I pull out the second ball, and then I pull the first ball out from behind my back and I have them next to each other. That should be the same situation. So the proof is to make this rigorous, with what I call a probability preserving map. Make rigorous. See, now that I'm looking at that, that looks like a dinosaur, which is wrong. I don't know. Okay, I'm going to leave it like that. Make rigorous with a so-called probability preserving map. Probability preserving map. And this is one way, anytime you have a symmetry, you can exploit the symmetry by making a probability-preserving map that uses that symmetry and do this stuff. I will say, this idea is great. It's very helpful. The proof is also great as you get into higher math. Also very helpful. But this is sort of like optional. We're not going to ask you. This is, if you want this as bonus content. We're not going to ask you to construct these probability-preserving maps. Sometimes you can do a shortcut, right? So like if this question was on an exam, we would expect you to do it for sure with method 1 and get the answer 3/5. If you know method 2, then you can skip some work. OK, so here is the probability-preserving map. What is it? It's a function, phi, and it inputs, phi inputs things in the probability space, things in the space, in probability space, and it outputs things in the probability space, equals something else, something else. I guess specifically in the sample space. Let me say the sample space S. In prob space S. These are elements of S. In math class, if you've been taking calculus, you'll see this before as phi maps from S to S. And so this colon and arrow notation means exactly phi is a function. It inputs things in the sample space and outputs things in the sample space. What is this function phi going to do? Phi is this cool Greek letter. Phi is going to swap ball 1 and ball 2. So in words, phi swaps ball 1 and ball 2. OK, and so more specifically, there are 4 things in my sample space. We drew them out over here. Red, red, white, red, red, white, and white, white. And the function phi is going to input one of these. Like, for example, it inputs red, white. It's going to swap them and output white, red. So I'm just going to write out exactly what phi does down here. So phi, there are 4 possible inputs. Phi of this, phi of that, phi of this, phi of that. And OK, let me see if I can draw the white ones. OK, phi of white, white equals white, white. Red, red is going to go there. Red, white is going to go here, and it's going to be white, red. And then here it's going to be white, red. And here it's going to be red, white. OK, so got to fill in the red balls. Red, red equals red, red. Phi of red, white equals white, red. Phi of white, red equals red, white. And phi of white, white equals white, white. So phi swaps the order. Phi is taking whatever happened on the second ball and taking whatever happened on the first ball and reversing them. Sometimes that does nothing if they were the same, but sometimes it actually swaps them. And here is the claim. This is the heart of the thing. Let's call it a theorem because that's exciting. Theorem. Phi is probability preserving. Probability preserving. What does probability preserving mean? It means if you do the probability of some event A, that is the same as the probability of phi of A. Actually, why don't we do it just for one element at a time? That'll be a little simpler to digest. OK, phi of omega is the same as the probability of phi of omega for all omega in S. So in other words, you're doing this function phi, and it's swapping things around, but it does it in a way where the probabilities are always equal. So even though phi mixes up the whole probability space, the probabilities don't change. And why is this true? The proof, the only one that is hard to check. So obviously, the probability of red, red is the same as the probability of red, red. The probability of white, white is the same as the probability of white, white. The only one that is maybe unclear are the off-colored ones. So the only case that needs to be checked is 2 opposite colored balls. And we already calculated both of these by the probability tree. We know the probabilities are the same. They are both 6 out of 20. You could also, without making the tree, you could argue that white, red has to have the same probability as red, white. That is the crux of this proof. The probability of white, red equals, I'll say notice the probability of white, red is the same as the probability of red, white, because they are both 6 out of 10, 6 out of 20. So the same. OK. And now that we have our probability preserving function, it's saying that there's a symmetry between the first and the second ball. This is like the math version of the idea. The idea says that there should be symmetry between the first and the second, and this is the proof. Like on the rigorous proof that there is symmetry between the first and the second is that the function phi that swaps them doesn't change. And then, so this is the final conclusion, is finally, the probability of R2 is the probability of phi of R2 by the theorem. So the theorem says that if you apply the function phi, the probabilities don't change. We proved it for every individual element, but that would also work for every set because every set is made of a combination of all the elements. So if you want to know the probability the second ball is red, well, you could instead find the probability that phi of the second ball is red. Those are the same probability by the theorem. And the probability of the second ball being red, when you apply the function phi to it, phi swaps the second and the first ball. So that is exactly R1. This is by the definition of phi. And what is the probability of R1? That's 3/5. So this is, we've sort of made our intuition rigorous by using this function phi, and it really does check that the probability of R2 is the same as the probability of R1 for this problem. The first and the second ball are symmetric. As long as you don't peak at both, then it's okay. So there you go. That's the idea, which takes 1 second. And then if you want to fill in the proof, it takes a little bit longer. As you get better and better at these things, you can sort of intuit all these steps. These are sort of very standard steps that you will, as you excel in your math career, you'll get better and better at these. Questions or comments about either proof? Actually, before I open for questions, let me ask you a question, which is, which one did you like better? And so I'll open that up. Let me give just 1 minute for this to give me your thoughts on taste for which problem style you like better, the straightforward one or the tricky symmetry one. Okay, and where did the timer go? Okay, questions or comments while people are voting? Yeah. 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 Yeah, so phi of red is the same as red. And so we've taken the first ball red and the second ball red and we've switched the two balls. But because they're both the same, nothing happens. And then therefore, in that situation, you don't need to check what's going on. Yeah. So that's a great question. And it's like, you really have to have all the definitions like in your head of what does it mean? Like, what is an element of the probability space? What does phi actually do? Which sometimes it takes a little more thinking than just solving the problem. Yeah, I think that's what you're noticing. Yeah, great question. Anyone else? Okay, perfect timing. Which one did you guys like better? Which one was the popular choice? I genuinely have no idea what people will say. Reveal. Okay, most people like the straightforward way. The thing about the symmetry way is once you get good at it, it's like, it feels like superpowers. So you just like, yeah, that's symmetric and that's symmetric. But it is harder to learn. So the straightforward way is nice because you sort of know what to do. That's the high school way of thinking. The symmetry way, you have to sort of like embrace your fear and be like, it's okay, I don't know it now, but I will know it later. So as you go further into math, I think you will, I'm hoping people will like both at least. Okay, that's nice, 16 people at least like both. I like neither, only one person. For a Friday morning, when I was a student, Friday morning, I think I would like no problems, but okay. All right, I'm gonna stop there. Professor Humphrey's gonna take over and tell us about other ways of representing probability spaces. So far we've done trees as the main one, and we're gonna see a few other options coming up right now.
Okay.
And we need the HDMI?
HDMI.
Wonderful.
Okay, so these are up on a pre-post there. I typically try to pre-post most of what I'm going to cover in class, but not every slide is up there, and often the pre-posts go a little further than I can possibly get in a class. So we'll see this. So we're going to start with these 2x2 tables here, and they're going to classify just 200 people by 2 traits. And we're going to call one of the traits event A and the other trait trait B. Now you can name the traits to be whatever you wish. You might be, event A might be the person has brown eyes, and B might be the person is enrolled in mathematical science. Who knows? Something like this. Okay? But we're going to get these, you can pick whatever events you want. Maybe you want to pick event A is male versus female, something like this, whatever. but we're going to obtain probabilities of various events for just a randomly selected person from this group of 200. So this group of 200 is kind of like 200 balls in an urn. But each ball has, again, not just one trait, in other words, not just red or white, but they've got two traits. And for each case, what we want to do is look at the relationship between the events A and B, and also between other relationships, such as between A and B complement. So let's start with our first table here. Okay, so we've got our 200 people. We've got them classified, and there's 150 show trait A, 50 show trait B. There's 120 show trait B, 80 don't show trait B. But then we've got all our intersections, and there's 90 people who show both trait A and trait B. There's 60 that show trait A, but they don't show trait B. There's 30 that don't show trait A, but they do show trait B, and there's 20 that don't show either trait. And so we've got these marginal totals there, and again, you know, when you look at those marginal totals, that's just the number that show trait A, that's the number that don't show trait A. Those numbers have to add up to the total of the 200 people, okay? So everybody okay on that table at the moment? Everybody's good on that table. So what we're going to do is...
I have a question.
Yeah.
You said it adds up to 200, but I added it up and I got 800. What did I do wrong?
What do you mean you added up to 800?
Well, I see. I learned, actually, my son is doing this app called Beast Academy, and they told us we should group things together. So I grouped these four together, and that was 200. And these were 200, and that was another 200, and then there was another 200 over here. So that's 800. 200, 200, 200, 200. But you said it should add up to 200.
Professor Nico, you are being very silly. These 90 people are included in those 150
okay.
people, and they're also included in those 120
Oh, I see now.
people,
Okay.
and they get included in those.
So it's not that
people.
there's yes or no or total. It's that total is the sum of the yes and the no. Is that this column is the sum of those two?
Yes, that is correct. Yes.
Okay.
Yes.
All right. Good. Good. Thank you.
Professor Nico was being very silly.
This is also what I tell my son when he makes a mistake.
Yeah. Okay. So let's just use those things, and I'm going to freeze it on one slide. Let me see. Which one do I want to freeze it? I'm going to freeze it on this one. And then we'll go to the questions. Very quickly, like, I'd say about 79 seconds would be appropriate to go through and calculate those probabilities from that table. Okay?
Can we give people some time?
79 seconds is about right.
Okay.
Maybe 81. Maybe 81. Yeah. And are you having a hard time seeing them there? Yeah, I don't know what to do about that, because if I switch the screens, then they won't be able to see. Now, have you got them posted? Did you get the pre-post?
No, I don't have it on here.
Okay, you could download the pre-post if you wish. Just thinking, strategically, you might want to get a seat a little closer to the center, or a little further back. We get a better angle.
I mean, I just got the pre-post now.
You got the pre-post? Okay. Ah. Have we done 81 seconds yet?
I could not tell you.
Let me just see how people are doing.
We can ask people to put their hands up.
Got them all done? Got them all done? Got them all done? Done? Not done? Let's do a couple of them anyhow. Probability of A. What did you come up with the probability of A? We should say 150 out of 200. Why? There's 150 people who have trait A out of the 200 people. Again, the people are picked at random, 150 out of 200. Probability of B. 120 people have trait B out of the 200. 120 out of 200. You can work it out. Now, the probability of A intersection B says that they have to have both trait A and trait B, and that's 90 out of 200. 90 have both traits. Probability of A given B. Oh, crap, they're giving me conditional probabilities. My brain. Oh, I'm given trait B. They have trait B. At this point, we restrict our sample space and say, okay, they have trait B. And now what's the probability that we get that they have trait A? It's 90 that show both out of the 120, which are trait B. 90 out of 120. Man, just an instant thing to solve. Oh, probability of B given A. Is that something different? Probability of B given A. Given that they have trait A, there's 150 that have trait A. Restrict us to this group here. 90 have trait B. 90 out of 150. Solved. Probability of A given B complement. Probability of A given B complement. Ooh, B complement. B complement. They don't have trait B. There's 80 of them, of which 60 have trait A. 60 out of 80. B given A complement. B given A complement. Oh, don't have trait A. Don't have trait A. How many have trait B? 30 out of 50.
You have to move your head.
I have to move my head.
That's the problem with that one. That makes that one hard.
That's right. It's really hard to see the numbers if my head's there. Yes, okay. 30 out of 50. And the probability of A union B, well, this is a little trickier here. A union B means that they have trait A or trait B, and that includes both. So that would include anybody who is in A or anyone who is in B. And a couple ways to think about that. We say that's 60 plus 90 plus 30, that's 180. Or you could say it's everybody except this group right here, those who have neither. Okay, so maybe we get that a little quicker by thinking of the complement. Okay.
Wait, I have another question. Remember, you did some of the sums for me. This was the totals, right?
Right.
So why am I adding up all these numbers when you already did it for me? Why don't I just do 150 people have A, 120 people have B, 150 plus 120 out of 200. 270, wait, 100. Why can't I add this number and this number to get the A or the B?
Now, what do you think?
I think maybe, well, the first problem is too many.
Too many.
Yeah, anyone have an idea? What did I do wrong? Yeah. Yes, okay, so there's a cool theorem called the inclusion-exclusion principle that says if you want to add it up, you got to do this one plus this one minus that one. And I forgot to do the minus 90. If I didn't know the minus 90, which is a theorem, I guess, how would you explain to somebody, why is it that this plus this is too much? Yeah. The 90 is, I double counted the 90, right? So I did 90 plus 60, and then I did 90 plus 30, and so I ended up counting 90 twice. To fix it, you can subtract off the 90. So if you wanted, you could do 150 plus 120 minus 90. That's another way to do it. Sometimes that comes up. Let's put that down as well. 150 plus 120 minus 90. And you could say the minus 90 is avoid double counting. That's a nice little trick. And actually, the main reason I tell you this is there's a very common mistake on the midterm is that people will add it up. They'll do 150 plus 120 and not realize that that's wrong. Okay, there we go. Got 3 answers to that one. Also, many questions like that on your homework, so good.
Okay, so those were our numbers. They're up there.
Now they're up there.
Let's unfreeze that one for the moment. And so we got those numbers. And then the next question was, are events A and B independent or dependent? And the answer is independent because notice that the probability of A is equal to the probability of B. If I know nothing about B, the probability of A is 0.75. But if I know that B occurs, the probability of A is still 0.75. In fact, if I looked at the probability of A given B doesn't occur, it's also 0.75. In other words, the probability of A does not change as we get this information of whether B occurred or didn't occur. There's no information provided by the occurrence or non-occurrence of B that tells us anything about the probability of A occurring. And you could work it in reverse too. There's many ways that you can check this. The probability of B, notice, is the same as the probability of B. Probability of B given A is the same as the probability of B given A complement. Or you could have said, if I multiply 0.75 times 0.6, that would be 0.45, which is exactly the same as the probability of the intersection that we got by direct count in the table. Yeah.
Isn't this a possibility where it's just like the numbers that were given for the 4 boxes that lead to this? Like if the numbers were different, would it change like wouldn't A not be A depending on B?
So I picked those numbers so they were independent. I picked those numbers. So that was very exact. So what you want me to do is look at case 2. Yes, you want me to look at case 2.
Wait, before we do case 2, I think there was one other question here.
Yes. We're going to do that. Absolutely. We're very excited to get to Venn diagrams. Yes, absolutely. Absolutely. Just another way of illustrating it could also be done as a tree. A couple ways of things. Multiple ways solving the same problem. Okay, so case 2. Hey, table looks very, very similar. But you talk about me being selective on my numbers. Selective on my numbers. Hey, notice that I've got the same row totals and column totals that I had before. Everything adds up to 200. The number of A's is 150. Not A's is 50. The probability, or the number of B's is 120. The number of not B's is 80. And so all those marginal totals are the same. However, the numbers inside have shifted a little bit. So what we want to do is work out those same probabilities now for case 2 here. Okay, so now you can move real fast. So we'll give you 73 seconds. 73 seconds to get these ones cranked through. Pardon?
They didn't memorize the numbers.
Oh.
Well, that's your fault.
Oh, that's your fault. Okay, yeah. So let's.
Now we have both on both. Table. That table's big enough for you today?
How did you do that?
I took a screenshot.
You are like a genius with this technology.
Screenshot.
I'll just warn you that if any day he doesn't make it to class, the class will not get recorded because I can never figure out the recording technology. We depend on him for technical expertise.
That's why there's 2 of them.
Exactly. So exactly what is my purpose?
You teach the mathematics, and then I take screenshots.
Oh, okay.
How many seconds did you want to give me?
73.
73. Okay. Presumably that was about 30 seconds ago.
That's about, yeah. Let's count it down. 43 minutes, yes. want to go at a nice pace at the same time. Wait, wait, wait. Wing. Okay, we're hoping at this point everybody says that they've got everything solved. Maybe yes, maybe no. But let's just flash up the answers here. And flash, flash, flash. That's what you should have got. Did I make any errors in there? Anybody see any bugs? Bugs looking good, looking good. Those look good to you? All look good? All looking good? Okay. So, you know, if you didn't get through them all, just make sure you work through them all carefully. Make sure you understand what all of those. Part of it is the business of just getting used to the notation. That's really a key thing. You want to make sure you're not confusing the probability of A given B with the probability of B given A with the probability of A intersection B. These are very easy things to get confused sort of early on in the game. But answering this question, are events A and B independent or dependent or not independent? Somebody give me an answer, what did you come up with? Independent or not independent? Not independent. Why? Give me a why. Give me a why. Why did he say they're not independent? Anybody want to give me a why not independent? Did you have a why not independent?
Probably for the same reason that the other one was dependent. In the case that the probability of A should be the probability of A divided by B.
A given B.
A given B, yeah.
Yeah.
And it's not.
And it's not. Right. So we had lots of ways of testing for independence here, and any one of them is sufficient to prove independence or that they're not independent. One way, probability of A doesn't equal the probability of A given B. We have updated the probability of A occurring given that we know that B occurred. It's a little more likely that A occurs if we knew that B occurred. But if we looked at the probability of A given not B, it's a little less likely to occur. Okay? If we look at the probability of B, 0.6, if A occurs, B's a little more likely to occur. If A doesn't occur, it's a little less likely to occur. Or if I had taken 0.75 times 0.6, again, that's 0.45. That intersection is not 0.45, it's 0.5. It's not exactly the right size. Yeah? It does change. How? Because there was only one configuration of numbers for those marginal totals where I would have independence, where the probability of A is equal to the probability of A given B, for example. And those had to be exactly the numbers. I'll just go flashback one back to the table, back to this table. If I was to look at, for example, the probability of B, 150 out of 200, that was 75% of these 200 individuals had trait A. But if I looked at only those who had also trait B, 90 out of 120, there were 75% of them that had trait A. For those who didn't have trait B, it was 60 out of 80. That's 75%. In other words, that 75% stayed constant whether or not they had trait B. And that's the only way I can configure that, okay? Any other numbers in this table? Any other numbers in this table that add up to the same marginal totals, we're going to get non-independence. Yeah? Well, it's not necessarily coincidence. But that's what would have to happen for us to get independence. Okay? Now, how are we doing on time? Okay. So we got those, we got the numbers, Okay, got the numbers, we went that. And we did that. So let's just do sketch Venn diagrams for case 1 and case 2. Okay, so sketching Venn diagrams, we'll go to the dot camera there. We'll go to the dot camera. And when you draw your Venn diagram, first of all, start with a box. It is horrendous to see Venn diagrams without a box. Because what that box represents, that one's kind of a bum pen, is the sample space. Why do I have so many crappy pens? Let's try this one. Okay, this one looks nice. Okay, that is our sample space. And then generally you're going to just start with 2 overlapping circles. We'll talk about refining these a little bit in the future, that we can do things with this to simplify. We're going to draw 2 circles. And, oh, his circles are so ugly. Yeah. I like my
Circle is overselling it. You got to call it a blob, and then
A
there's
blob.
no pressure on you
to make it,
to make it good.
yeah, make it.
And then if like later on in the problem you need it to twist around in some weird way,
Okay.
you're okay.
So Professor Nika may label things a little differently than I do. Let me show you how I label things. So we're going to do case 1 here first. And total area of the sample space is 1. I label my A's and my B's outside of the circles, because if I put it inside, it's not clear whether it's referring to the whole circle or just the piece. So I like to go outside, and then I'll put my probabilities there, like so. And you'll notice that the sample space consists of 4 intersections. This is really critical. There's 4 mutually exclusive and exhaustive intersections. Other words, any individual is going to have to belong to one of the 4 intersections in this sample space here. And if they share both A and B, we are going to be in the intersection A intersection B. If they have A, but they don't have B, we're going to be in the intersection A intersect B complement. If we are in this intersection, what is this intersection? This is A doesn't occur and B occurs, but what about the individuals that have neither A nor B? Oh, they're outside. Okay, so they're in the intersection A complement, intersection B complement. Okay? And then we can go through and label our probabilities there. And we worked out the probability of A intersection B being 0.45. And the probability of A intersect B complement, well, you know, I could go work it out again, etc. But hey, 0.45. If it's 0.45 in here, it's got to be 0.30 in here. And 0.6 minus 0.45, I got to be left with 0.15 here. And what's left outside? 0.75, 0.9. Oh, this is going to be 0.20 out here. Okay, so just a second. Did I add that up right? No, I didn't. Did I do something wrong?
0.75. No, looks good to me. Wait, I guess it should be 0.1, not 0.2.
Yeah, it should be 0.1. Should be
Okay.
0.1.
I think you said 0.1 and you wrote 0.2.
Okay, that was very silly of me. Okay, so you double check that your probabilities add up to 1, and we've worked out the case 1. Now at this point, we have hit 20 after 10.
Gary, I'm gonna quickly show you my artwork. Are you ready? I drew my blobs sideways for case 2. See, sideways blobs, and then it kind of looks more like the table. Same information, sideways blobs.
Sideways.
We'll take up the sideways blobs on Monday. All right, have a great weekend, everyone.
If you get a chance, try to sketch out the case 2 Venn diagrams. Just make a couple.
Make sure you do your homework due at midnight tonight if you haven't done it yet. Should be an easy one.